What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 13, Section 5, Counting Principles. Let's do it. For the following exercises, assume there are n ways an event A can happen, m ways event B can happen, and that A and B are non-overlapping. So it says, use the addition principle of counting to explain how many ways event A or B can occur. So when we see this word or in the middle, right, what we're doing to calculate this is we're simply taking the sum of m and n, meaning the amount of ways A and B can happen, right? So the answer would be m plus n. That's how you do it. Done. When given two separate events, how do we know whether to apply the addition principle or the multiplication principle when calculating possible outcomes? What conjunctions may help determine which operation to use? So what they're referring to is the addition principle should be thought of when you see or, right? Then we're talking about the addition principle. And when we see the word and, okay, now we're thinking multiplication principle. And that is how you do it. Done. What is the term for the arrangement that selects R objects from a set of N objects when the order of R objects is not important? What is the formula for calculating the number of possible outcomes for this type of arrangement? Okay, so what this is talking about when order is not important is what's called a combination. And the formula for calculating the number of combinations is going to be n factorial over n minus r factorial times r factorial, where n is the total number of objects and r is the number that you're choosing from n. And that's how you do it. Done. Let B be this set. How many ways are there to choose a positive or an odd number from A? So what we want to look at is how many positives are there. We've got 1, 2, 3, and 4. And then we want to look at how many odds we have, which are 1 and 2. And the way that we can get a positive or an odd is going to be, now we see that word addition, now we see that word or, so we're thinking addition principle. So we got 2 and 4, add them together, and there are 6 ways to choose either a positive or an odd. That's how you do it. How many ways are there to pick a paint color from 5 shades of green, 4 shades of blue, or 7 shades of yellow? So again, we see that word or, we're thinking addition principle. So it's simply 5 plus 4 plus 7, which is 9 plus 7, which is 16. So there are 16 ways. Done. How many outcomes are possible from tossing a coin and rolling a 6-sided die? Notice the word and here, right? So how many outcomes are there from tossing a coin? There are 2 outcomes. And how about a 6-sided die? Well, of course, 6, and the operation now is multiplication, which means there are 12 possible outcomes. That's how you do it. Done. How many different ways are there to construct a string of 3 digits if numbers can be repeated? So we think about 1, 2, and 3, right? And what are they really talking about? Well, they're talking about these all together, and they can be, if they're digits, right, it can be anything from 0 through 9. So 0 through 9, there's 10 options here, there's 10 options here, and 10 options here, and there's no restrictions, right? So to get the total amount of possibilities, we take the product of these, right? 10 times 10 times 10. And 10 times 10 times 10 is 10 to the third, or 1,000 different ways to construct a string of 3-digit numbers. And that makes sense because there's 1,000 numbers from 000, right? Basically 0, all the way up to 999. So that's how you do it. Done. For the following exercises, compute the value of the expression. So this is a permutation, and the formula for a permutation is n factorial over n minus r factorial. And your n value is the first value, the 5, and the r value is 2. Okay, and the n value is the first value, and the r value is the second value, which is 2. So now we're going to plug and chug. We've got 5 factorial over 5 minus 2, which is 3. Factorial. So again, just a quick reminder, what is factorial? It's that multiplication countdown, 5, 4, 3, 2, 1, all the way down to 1, multiplying. And for 3 factorial, it's 3, 2, 1, again, a countdown. And you'll notice cancel, 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 right? We're left with 5 times 4, which is 20. And that's how you do it. Done. For this one, because it says P, we're taking a permutation calculation, which is n factorial over n minus r factorial. And we're going to plug in 3 for n and actually 3 for r as well. So on top, we get 3 factorial over 3 minus 3, which is 0 factorial. So you might say, well, this is dividing by 0. This doesn't exist. But in fact, 0 factorial is 1. Okay, and 3 factorial is 3 times 2 times 1, which is 6, which means our final answer is 6. Done. For this one with the P, we're calculating a permutation where 11 is the n value and 5 is the r value. So we've got n factorial over n minus r factorial, like so. We're going to plug in 11 for n, and we're going to plug in 11 minus 5 down here, which is 6 factorial. Okay, so what is this going to be? Remember, it's a multiplication countdown, but you'll notice that since we have 6 factorial on the bottom, everything from 6 onward for the 11 factorial is going to cancel out. So we can simplify this as 11 times 10 times 9 times 8 times 7. And as I mentioned, 6, 5, 4, 3, 2, 1 is going to be on the top and the bottom, so they're going to cancel out. All right, now we can calculate this. 7 times 8 is 56, times 9 is 450, is 504. And then times 10 is 5,040. Obviously, you can do this in a calculator, but we'll just do it by hand since we're already here. And then 11 times 5,040 is 5,040 plus 50,400, which is going to give a final answer of 55,440. That's how you do it. Done. So this one is a combination where C is n factorial over n minus r factorial times r factorial. So very similar to a permutation, we're just adding an extra r factorial here. Again, this is going to be n, this is going to be r. So let's plug and chug. We got 12 factorial on top over n minus r, 12 minus 4, which is 8 factorial, and then times r factorial, which is going to be 4 factorial. Okay, we can calculate this out, but I'm going to actually use Desmos to do so. So once we calculate everything out, we get a value of 495. So 495 is the answer. Boom, done. So this one is a combination, and 7 is the n value, 6 is the r value. So the formula for a combination is n factorial over n minus r factorial times r factorial. Okay, so we've got 7 factorial over 7 minus 6, which is 1 factorial, times r factorial, which is 6 factorial. All right, so right off the bat, I know that 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. 6 factorial is similar, it's just 6 and down, right? So we can see that everything after 7 is going to cancel out with 6 factorial. We're going to be left with a 7 on top. 1 factorial is, of course, 1. So that means our final answer here is 7. Done. For the following exercises, find the number of subsets in each given set. So when we're trying to find the number of subsets, we look at the number of items in this set, and we say 2 to that power. And since there's 10 here, we say 2 to the 10th power. 2 to the 10th equals 1,024. So 1,024 is the winner. Done. So for this one, we're trying to find the number of subsets when we have 5, 4, and 3 different values. And so that's a total of 12 values. So in this case, we're going to say the number of subsets is going to be 2 to that 12th power, which is 4,096. So 4,096 is the winner. Done. The set of 2-digit numbers between 1 and 100 containing the digit 0. Okay, so what we're going to have there is, let's write out that set. We're going to have 10, 20, 30, 40, 50, 60, 70, 80, and 90, right? So these are all the 2 digits containing 0. Now, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So what we're going to do is, to get the number of subsets, it's going to be 2 to the 9th power because there's 9 terms, and that is 512. So 512 is the answer. Done. So for this one, we're trying to find the number of ways that we can arrange these letters. Academia. Now, we've got 1, 2, 3, 4, 5, 6, 7, 8 different letters. Now, obviously, we see that we have multiple A's, so that's something to bear in mind. But we're going to start with that number 8. And we're going to say it's 8 factorial. Then, since we have 3 A's, for example, nothing else repeats, but we got 3 A's, we're going to divide it by how many times that A repeats, which is 1, 2, and 3 times. So we got 8 factorial divided by 3 factorial. And we're left with 6,720. So we can arrange this in 6,720 unique ways. That's how you do it. Done. So for this one, to figure out the number of arrangements, we're going to see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different symbols. So we're going to start with 12 factorial, but then we have to factor in the fact that we've got repetition of these, and these. So for this one, we have 3 of those same symbols, so we're going to divide by 3 factorial times that one. We have 2 of those, 2 factorial. Here we have 3, so 3 factorial, and here we have 4, so 4 factorial. All right, let's plug this into Desmos. So we're left with 277,200 different ways to arrange these symbols. So 277,200 is the answer. Done. The set S consists of 900 million whole numbers, each being the same number of digits long. How many digits long is a number from S? Use the fact that a whole number cannot start with the digit 0. So for this one, I'm going to say that the number of digits is actually going to be the same as this, right? So 900 million, we're going to have 9 digits. So let me show you why. If I write out 9 slots here, think about the smallest value with a 9-digit number that I can get, which is 100 million. Okay, so this would be on the small end. What about on the large end? We'd have 999,999,999. Now let's think about what are all the numbers that are in between in this set, right? Well, from 100 million to 199,999,999, right there, that's going to be 100 million values, right? So 100 million just from 100 to basically 200 million. Then you have another 100 million up to 300 million, 400 million, etc. Meaning that once we get to 999 million, we've now gotten this full 900 million numbers. So the answer, therefore, is 9 digits. That's how you do it. Done. Can C n of r ever equal P n of r? So basically, can a combination ever equal a permutation? So if we look at the formulas, let's see, let's check them out. Let's set them equal to each other. So combination is n factorial over n minus r factorial times r factorial. And a permutation is n factorial over n minus r factorial as is, right? So where I would say that these two would be equal is whenever r is going to be 1, because if r is 1, it's essentially not doing anything. We can get rid of it, and then the two would be equal. So when r equals 1, they are the same. Done. How many arrangements can be made from the letters of the word mountains if all of the vowels, must form a string? So if the vowels O, U, A, and I, if those are going to be a string, they're all going to be together. You can almost think about it as one big letter. So really we have an M, N, T, N, S, right? Those are really the letters. And then we have this vowel string. So we do have 2 of the same. We have to remember that. And then we also have in total 6 letters if we think about this vowel string as one letter. So we start with 6 factorial, but again, we have to divide by 2 factorial because there's 2 n's. All right. But then we have to think about this string, right? So yes, we have a string of O, U, A, I. Those are all unique, right? O, U, A-I. And then we have to think about all the different arrangements of the string, right? O-U-A-I, O-A-U-I, etc., etc. How many arrangements are there? There's 4, because there's 4 letters, factorial. So then we take this final answer, multiply it by 4 factorial. So here we get 8,640. So there are 8,640 arrangements. That's how you do it. Done. A cell phone company offers 6 different voice packages and 8 different data packages. Of those, 3 packages include both voice and data. How many ways are there to choose either voice or data, but not both? So the way we can think about something like this actually is with a Venn diagram, okay? So we'll make a little Venn diagram, and we've got voice packages and we've got data packages. And this would be the packages that include both. So we could say 3 packages include both voice and data. And then since this entire circle includes everything voice related, if there are 6 total voice packages, there would be 3 that are just voice. And since this whole circle is data, since we've already got 3 here and 8 total, there'd be 5 out here, which means that for the just voice packages and just data packages, we've got 3 and 5, which add up to 8. That's how you do it. Done. A wholesale t-shirt company offers small, medium, large, and extra large in organic or non-organic cotton with colors white, black, gray, blue, and red. So how many different t-shirts are there? All right. So we got 3 different categories, right? We got size, we've got organic or non-organic, okay? And then we've got color. So in each category, let's see how many options we have. For size, we have 1, 2, 3, 4. Organic or non-organic, that's 2 options. And then the colors, it looks like we've got 5 options. So to get the total amount using the counting principle, what we're going to do is we're going to take the product of these. 4 times 2 times 5. That's 8 times 5, which is 40. So that means there are 40 t-shirts to choose from. That's how you do it. Done. An art store has 4 brands of paint pens in 12 different colors and 3 types of ink. How many paint pens are there to choose from? So we think about, we got brands, we've got colors, and then we've got types of ink. And we're going to put the numbers of each 4, 12, and 3. And using the counting principle, we're going to take the number of options in each category, since we're taking a mixture of all 3 for every type of paint pen, and we're going to multiply them. 4 times 12 times 3, that's 48, times 3 is 144. And that's how you do it. 144 is the winner. Done. How many ways can a baseball coach arrange the order of 9 batters if there are 15 players on the team? So this is a permutations question, right? Because we care about the ordering. And all we have to do is identify the n, which is 15, that's the total, and the r, which is the number we're choosing. Remember that the formula is n factorial over n minus r factorial. So this is just for a permutation. Okay, so we're going to have 15 factorial over n minus r. That's 15 minus 9, which is 6 factorial. Let's see what that is in Desmos. And here we get this huge number to the 9th power, which is in the billions. And writing this in regular notation, it's 1,816,214,400. So that's your answer. That's how you do it. Done. Motorcycle shop has 10 choppers, 6 bobbers, and 5 cafe racers. Different types of vintage motorcycles. How many ways can they choose 3, 5, and 2 cafe racers for a weekend showcase? All right. So we're talking about combinations here, because we're not talking about ordering. We're not talking about putting it in a particular arrangement. We're just talking about choosing. So when we're talking about combinations, let's do it one by one. So first we're going to take the number of combinations for the choppers, right? And don't forget, our combination formula is n factorial over n minus r factorial times r factorial, where n is the total, r is the amount we're choosing. So for choppers, it's going to be 10 factorial over 10 minus 3, right? We're choosing 3, that's 7 factorial, times r factorial, which is 3 factorial. Okay, so this is for choppers. I'll put a C here. Then for the bobbers, we've got same formula, 6 factorial over 6 minus 5, right? That's the difference, which is 1 factorial. And then times r, which is 5 factorial, right? And then we've got the cafe racers. Let's do r for that. And then here we have 5 for the n, because there's 5 total, 5 factorial over 5 minus 2 factorial. That's the r for cafe racers. So 5 minus 2 is 3 factorial times r factorial, which is 2 factorial. All right, I hope that made sense. That was a lot of the word factorial. But now let's take these, and then if we want all the ways, we can choose all 3 of these. Now we have to take the product of all of these, because we're looking at the arrangements, the unique arrangements now, or unique collections we can make, knowing that there's a total amount of those combinations, the bobber combinations, and cafe racer combinations. So let's plug this into Desmos. And once we plug everything in, we get 7,200. So the answer is 7,200. That's how you do it. Done. Just for Kicks Sneaker Company offers an online customizing service. How many ways are there to design a custom pair of Just for Kicks sneakers if a customer can choose from a basic shoe up to 11 customizable options? So this is a subset question where the formula for calculating the number of subsets is going to be 2 to this power, right? Because there are these 11 different options. So we're going to say the answer is going to be 2 to the 11th. Let's check out what that is in Desmos. This is going to be 2,048. So 2,048 is the winner. Done. Suni bought 20 plants to arrange along the border of her garden. How many distinct arrangements can she make if the plants are comprised of 6 tulips, 6 roses, and 8 daisies? So this is almost like a arrangement question when we have letters and repeat letters, right? It's almost like we have 6 A's, 6 E's, and 8 R's, something like that, right? So we have to account for the repetition. So we're going to start off with saying we've got 20 factorial, right, in terms of all the different types of arrangements. But then to account for the repetition, we've got to divide by 6 factorial for the tulips, 6 factorial for the roses, and 8 factorial for the daisies. Let's see what this is in Desmos. So here's our answer, 116,396,280. So that's the final answer. That's how you do it. Done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.